Thank you very much for the very nice, very kind introduction, Hugo. A bit of pressure to try and deliver to some of those nice things you said. Can you see my screen okay?
Yes.
Okay, fantastic. So look, thanks so much for the invite. It's great to be here. I always love talking about some of these exciting topics. The title of my talk is a little long. It takes 3 lines, but yeah, it's basically a brief overview of autonomous vehicles as we stand in 2022, and including touching on a little bit of detail their mapping and positioning systems. A bit of an overview about what I hope to cover. I'll do a very brief introduction, mainly because I'm trying to generate some return business for another talk at some stage in the next few years. I'll give a very brief history of autonomous vehicles, talk about their key components, focusing on the mapping and positioning systems, but sort of covering the whole package of what's needed to make them work. Talk a little bit about the current state of play in autonomous vehicles and touch on the future. Now, I give a lot of different types of talks, and I sort of conferred with Hugo and Kate and Claire. And so I imagine for some people, this will be frustratingly light in deep technical detail, in which case blame Hugo and Kate. But I'm always happy to come back at another time or another venue and give a more technical talk as well. So I come from the Queensland University of Technology, which is the other university in Brisbane on top of the University of Queensland, which is where I used to be. It's very confusing because it's basically just the words switched around. We need to work on that from a branding perspective. But I co-lead a large robotics lab there. We do, if it's a robot or an autonomous system and it moves or navigates in the air, underneath the water, on the ground, even deep underground in mine sites, we work on projects in those areas. And we go all the way from fundamental research to very applied commercial research with many industry and government partners. My own research career has been focused primarily around biologically inspired robot mapping and navigation, which is where I've intersected paths many, many years ago, first with both Hugo and Kate and many other amazing researchers in the UK. I'm not going to talk about this at all today, but just to highlight that we've done sort of almost 2 decades now where I was involved, and this work was happening before I was involved, on modeling at varying levels of fidelity how we think, or how our illustrious neuroscientist colleagues think that many natural organisms map and navigate the world, and trying to make robots better systems because of that. But I won't talk about any of that in detail. It's just a teaser of what we've done. The other thing that's really relevant looking sort of more forward is for the next 5 years, I'm extremely fortunate to have received a very large Australian funding grant to basically have a crack at developing a complementary and alternative ubiquitous positioning technology to GPS. So basically trying to create some redundancy. So if, for some reason, and there's multiple reasons this occurred, GPS drops out permanently for long periods of time, we have a viable universal alternative positioning technology at hand. And that will draw upon biologically inspired techniques, but also addresses these other things that aren't as addressed in mapping and navigation research, especially in robotics, like trusted systems, auditable systems, systems that are privacy compliant and cyber secure, and so forth. In the autonomous vehicle space, which is what I'll talk about today, we do a lot of work. This is just my group's involvement, but my colleagues are involved in a large number of other autonomous vehicle projects. So we work with companies like Ford. We work with our local government extensively, I guess, which is also the case in the UK. You see companies like Oxbotica and other ones working extensively and sort of providing advice to the national government. So we do that as well. We work in mining, in defense, and a number of other areas. And we do a lot of outreach and engagement because we believe it's particularly important with these exciting, but sometimes scary new technologies to make sure the public is well informed, because a lot of the fear sometimes or skepticism comes from a lack of deep sort of intuitive understanding of what the technology actually could bring. And so our job as academics is to make sure that's not an issue. And one of the awesome perks of my job, although it hasn't been so much the last couple of years because of travel, is I get to go around the world and get rides in autonomous vehicles or see autonomous vehicles all around the world, which is a fabulous perk. And you see very interesting cultural differences. So if I'm in San Francisco and I'm getting a taxi or an Uber from the airport and I see an autonomous vehicle, I'm leaning out the window, taking photos, I'm very excited, and my Uber driver just doesn't care because they've seen so many. Whereas in, say, France, where I see an autonomous shuttle, for example, my Uber driver also hasn't seen an autonomous shuttle before. So they're also leaning out their window while driving me, trying to take photos. And so it's a very nice perk of the job. So what's in an autonomous vehicle? This is one photo taken on public roads. You've got the basic sensors. You can judge the maturity of an autonomous vehicle by how visible the sensors are. The more hidden the sensors are, or the more streamlined they are, it's likely that the autonomous vehicle has gone through a lot of different generations of development. The system has onboard artificial intelligence, essentially, to help it drive, somewhat like a human. And there's a joke in Silicon Valley that, how do you tell if a vehicle is autonomous? Well, if it's got two safety drivers in it supervising it, you can tell it's an autonomous vehicle. It's not a particularly good joke, but it's indicative of the current progress in the field. It's important to note, people talk about levels of autonomy, 0 being what humans drive a car now, and level 5 being an autonomous vehicle where the human probably couldn't even drive or take over, even if they wanted to. It's important to not get too bogged down in these definitions because they are fuzzy and imperfect, but it's good to have a working awareness of them. And why autonomous vehicles? Why any big technology? Well, it's really around money, and potential health and transport benefits, plus hundreds of sort of secondary and tertiary potential benefits as well. It's also important to note that autonomous vehicles have been commercially deployed for many years already in a very select range of non-road environments, especially mine sites. And so these aren't just a sort of novel technology concept, they are helping major multinational companies be financially competitive in the mining industry. So they're actually an essential part. So the motivation, there's various figures have been bandied around, but people have been, or this has been dialed back a little bit, talking about sort of $1 trillion markets over the next 10 years about self-driving cars. So these are pretty big financial figures. And of course, there's the health and safety benefits. So globally, it varies, but there's around 1 million, a bit over 1 million automotive related deaths every year, and there's a much larger number of injuries. And so if you have the potential to reduce that, that would be transformative. Now, there's a bunch of asterisks or conditions on that, which I'll get to, because it's important to be representative of these new technologies. So this is one of them. If you deploy autonomous vehicles, they're going to be driven primarily by companies who want to make money. And so they would probably be deployed in high revenue areas, so affluent, first developed nations. But the per capita road tolls are typically lowest in those countries. And so it's possible that this technology, which could massively reduce the road toll, would initially be applied in the regions where it would make the smallest difference. And so it's always important to present an accurate picture that this technology could be beneficial, but it's not always straightforward. So I won't go through the detailed history of autonomous vehicles, noting that the concept of autonomous vehicles has been around for many, many years, dating back to even before the 1939 World Fair in New York, where it was a concept. But modern autonomous vehicles sort of started in the 80s. So CMU did a lot of work. This is one of their early NavLab autonomous vehicles. And it's very big, and it's moving very slowly because it's full of computers in the back. And this is about the limit of the compute of the day. So this is sort of the first step. Note the date, this is 1986 approximately. By 1996, people were driving pretty reliably on highways autonomously. And so people were starting to try and cross the United States, for example, with an autonomous vehicle, and they could do it pretty well with minimal interventions. So highway driving has always been one of the first targets for autonomous vehicles. The real, I guess, modern kickstart to autonomous vehicles was in 2004, 2005. So the US Defense Agency, DARPA, ran this amazing challenge in the desert where autonomous vehicles had to navigate around 200 kilometers, a bit over 200 kilometers across the desert autonomously. Now, they were given course GPS waypoints that they had to try and hit. But apart from that, it was autonomous. So you can see the vehicles at the start line here. You can see modified Humvees. And behind them, you see a vehicle of extremely nervous and stressed roboticists and engineers watching their pride and joy go off fully autonomous on the course, so that you can see the vehicle there. Now, in 2004, none of the vehicles made it more than, I think, about 11 kilometers on the 200 kilometer plus circuit. In 2005, I think 5 or 6 vehicles completed the course successfully. I think 5 of them within the time limit. So this is the winner from 2005 from Stanford and a range of other organizations. And so in 1 year, they made incredible improvements in autonomous vehicle. And this was one of those challenges that really captured the public's imagination at a big scale. They did an urban challenge in 2007. They wanted the vehicles to be able to navigate around and understand traffic in cities. There was some amusing sort of low-speed prangs, but once again, a lot of progress made. And so that was 2007. So that's 15 years ago. And that kicked off huge amounts of investments and excitement that has endured to today in autonomous vehicles. So what's the key components of an autonomous vehicle? Sensing is one. So there are lots of cool sensors that are used for things like navigation on an autonomous vehicle. You use GPS where available, the global positioning system. It is useful for planning a journey across a city. It is not relied on to provide millisecond by millisecond precise positioning in a city, because you can't rely on it for something like that. So you wouldn't use GPS to do precise lane keeping inside a tunnel, for example. It's just not a fit for purpose, but it is useful for certain things. Radar is another sensor which has been on cars for many years now for things like collision avoidance. It has key characteristics that it can see through, to some extent, fog and smoke and weather effects like rain. And it's very useful as a last-ditch collision avoidance system, whether your car is autonomous or not. And for the more animal-focused people in the audience, you can sort of be thinking about the analogous sensors that exist in the natural kingdom. LiDAR is what you'd call the crown jewel of autonomous vehicles. So this is a sensor that sits typically on the roof of the car and tells you the range to sort of millimeter or centimeter precision to all the objects in a 360-degree view around the car, up to 100 or 200 meters away from the car. It's an absolutely incredible sensor. It has been very expensive. The price has gone down a little bit, but it's almost, it isn't cheating, but it is an incredible sensor. And if you look at the maps you get, this is from several years ago when I got a ride in one of the cars at Google, you can see you get a very nice view all around the car. And all of these sensors, there's innovation happening continuously. Obviously, things like smartphones have driven a lot of innovation, but autonomous vehicles are also driving a lot of the demand. So there's an Australian company called Baraha, for example, which is creating new types of LiDAR type sensors. And there's many, many others around the world. Vision is probably the most interesting sensor, but I'm biased. So you have vision is arguably the primary sense that humans use, and it's the same for autonomous vehicles. Vision is used heavily, gives you very rich information about the environment, gives you a potential very deep understanding of the environment, but is also affected by things like weather, snow, nighttime, bad lighting, and so forth. So once again, it's not a get out of jail free card. You have to do clever things with how you process sensory information. And a typical autonomous vehicle will have a bunch of cameras on it, whether it's a Tesla or another more experimental vehicle, and the cameras will do different tasks. So you might have a camera that has a very small field of view and a relatively high zoom lens on it, and you might use that specifically to spot traffic lights or traffic signs from a long way away. Once again, thinking about how this relates to nature and animals and insects that might have different types of eyes. Some have many different types of eyes. So there's some analogies there. And there's lots of other sensors. These are not so glamorous, but you have accelerometers, you have things that measure the power draw or the throttle levels of the vehicle and so forth. And all of these are used in a typical autonomous vehicle system. So what do these things look like in the wild? So these are, because I haven't been able to travel so much recently, these are mostly photos I've taken myself as I've been eyeballing autonomous vehicles in the wild, so to speak. But you can see some typical sensor arrays here. And most of these are from America, although a few are from the UK as well in later slides as well. So you can see sensors are a very critical component. To not focus entirely on autonomous vehicles, I mentioned that the actual only commercial deployments of autonomous vehicles are typically in off-road environments. So this is a project that we worked on with a number of companies, including Caterpillar, creating autonomous navigation technology for underground mining trucks. So these are 10, 20, 30-ton trucks. They're already autonomous, so we were trying to create improved positioning and mapping systems for them, relying on vision and LiDAR sensors. And this is the sensor rig that goes on the truck. And in these underground environments, it's very, very challenging. Rocks fall, dust fall. There's all sorts of different lighting conditions. The sensors can get wet. And so they get very dusty and banged up very quickly. And just to give you an example of a different type of autonomous vehicle. So sensing is the way that an autonomous vehicle sees and senses the world, but sensing is not much good without some sort of ability to process what the car is seeing. And so that's where we talk about what we'd call the onboard driving intelligence. So I won't go into any of these except the positioning and mapping piece in a bit of detail, but scene understanding is a key component here. So the robot or the autonomous vehicle is looking at the world around it, and in order to be able to drive effectively, it needs to be able to have a sophisticated and accurate understanding of what is happening in the world. So not just what is in the world, like pedestrians, cyclists, and vehicles, but what those pedestrians or cyclists or vehicles are doing, where they are moving, where they are predicted to move. These are things that humans do pretty well effortlessly, but which are incredibly difficult to get an autonomous vehicle to do reliably in all situations. And although there's a lot of traditional mathematical-based approaches to traditional control-based approaches to these systems, increasingly what we call deep learning, so modern, very big neural network-based artificial intelligence, is playing a key part in many aspects of this. And this is arguably, I guess, still one of the hottest fields in all of computer science. It's the only way computer science venues can compete with your nature and science venues in terms of impact and citation metrics, and is driving a lot of the autonomous vehicle race. So what's the positioning and localization and mapping piece for autonomous vehicles? So this is what my group specializes in, and we could do a whole day workshop on it, but I'm going to try and cover a couple of the key concepts here, hopefully is enough to generate some questions. So the first question for people creating mapping and navigation systems for autonomous vehicles is the to map or not to map question. And so option one on the left is the mapless system. And so the idea here is the autonomous vehicle does not have a specific prior map of the environment it's operating in. It might understand roads and understand all the aspects of an environment, but it doesn't have a location-specific prior map or representation or database of the environment that it's operating in. And so most famously, this is the approach that companies like Tesla are taking, but many of the other companies are going with option two, which is the use of prior maps. So you make sure that the vehicles operating in your environment already know about the environment. Now, what a prior map constitutes has infinite variations, but the key is it already knows stuff about the specific environment that it's operating in. Now, humans, just to point out the obvious thing, humans don't need a detailed prior map of an environment. You can get off a plane jet lagged in a city you've never been to before, even without GPS, and probably do a rudimentary job of driving a vehicle around. So there's obviously this proof of concept that humans don't need detailed prior maps. And the big tension here is that autonomous vehicle technology is not emulating exactly how humans drive a car, and therefore is having a prior map a necessary deviation from how humans do it that's needed to make the technology work. So prior maps might look something like this. This is a very detailed 3D map from, I think, San Francisco. This is not that different to what a lot of autonomous vehicle maps would look like. You get this beautiful three-dimensional map of all the things in the environment, plus some textured information about what they look like. Obviously, would take a lot of compute power, a lot of storage as well to store and maintain these maps. They're often referred to as high definition maps, although this definition is fuzzy, as many definitions are. A high definition map can consist of a number of things. It could be basically a glorified version of the map that you use on your Android phone or Apple phone or other brand of phone, which is basically that street map plus some annotations that says sort of left turn here, right turn here, and so forth. Or it can be that super detailed map you see at the top right. And these maps can consist of a number of different layers. Some of these layers can sort of be long-term static maps. There can be geometric elements of the map. There can be semantic or contextual elements of the map as well. And there can be real-time elements of the map, which are tracking the vehicles and the pedestrians as they move around the car. So it's quite a sophisticated structure. There is no correct answer to this yet. So each company has a slightly different version of this. But this is generally what people are talking about when they talk about HD or high definition maps for autonomous vehicles. Now, if you do rely on maps for an autonomous vehicle solution, which is what most people do, you have lots of challenges. The maps give you a key advantage in that you know what's in the environment, but they also introduce a bunch of additional challenges. So it's, once again, nothing is ever very simple. So when you create the initial maps, you can always muck it up. So your map that you create, however you create it, can be imperfect or inaccurate in places. The world is not a nice, perfect simulation environment. It's always changing. And so you need some way of representing that and accounting for the fact that the world may have changed, even in a very short period of time. A map is only useful for an autonomous vehicle if the autonomous vehicle knows where it is located within the map. So this is the localization or positioning piece. And this doesn't always work perfectly as well. When you go to update the map, you may update the map incorrectly and corrupt the map, and maybe not realize this until later on. And then a range of other errors. And so we've been working on sort of reviewing these issues, including working with our local transport and government organizations, as most academics in their respective countries are doing around the world. Once you have your map, so you have a map or representation of the world, there are lots of different positioning techniques or types of positioning. So absolute positioning is what we'd refer to as a global coordinate that tracks where you are in a global map of the world. So you can imagine this a precise latitude, longitude position in the world. It's obviously useful for planning your journey across town. It is not necessarily used as much for other things like local control of the robot over a sort of 1 second period. Relative positioning is different in that it's the car, the autonomous vehicle, knowing precisely where it is relative to other vehicles and infrastructure in its locale, so just in its local area. And this is, relative positioning is very important for making sure the car doesn't hit other cars, doesn't hit pedestrians, stays in its lane correctly, stops at the right point at the traffic lights. There is some sort of overlap between relative positioning and absolute positioning, but they do also serve very different purposes as well. But those aren't the only types of positioning. So another type of positioning is what we'd call contextual positioning. So this is not knowing the absolute longitude coordinate of where you are in the world. This is having an understanding of the nature and type of place or location that you're in. So in an indoor context, it could be, I know I'm in a kitchen versus I know I'm in a bathroom. These are different types of places. In an autonomous vehicle context, it could be I'm in a forest road versus I'm in a busy city environment, I'm at a rail crossing, or I'm in a snowy highway environment. So these are not unique specific places, but they're types of places that the car might use as context. What would you use this contextual positioning for? Well, your car isn't just doing navigation and mapping, it's doing things like recognizing people, recognizing other vehicles in the environment, driving to the conditions, for example. And in this case, having place type specific behavior is potentially an important part of the solution. So you can imagine on a desert highway, you would learn an expectation that you're typically not going to be surrounded by traffic, and you're typically not going to have lots of pedestrians around. You still have to watch out for them, but there is that prior context. Whereas if you're driving through the nightclub district of your town at 1 a.m. in the morning, you can expect a lot of intoxicated people who aren't really paying attention to your vehicle and probably jump out in front of your vehicle. And I always joke that driving through the clubbing district or bar district of your town at 1 a.m. in the morning is a great test for an autonomous vehicle. Obviously, you'd want to make sure it's entirely safe, but humans are in a particularly unpredictable behavior pattern at that time. Another key concept, which isn't addressed as much in autonomous vehicles publicly, although I'm sure all of the commercial companies are doing this behind the scenes, is this notion of positioning integrity. And so integrity as a concept has been, of course, very heavily looked at in other sectors like the aviation industry, because the safety piece and the reliability piece and the integrity piece is so incredibly critical when you have 300 or 400 passengers on a plane. And there's a lot of fuzzy terms here, but there's issues like trust. So can you trust the mapping and positioning system on your vehicle? Can you characterize the performance? So under all situations that the vehicle may encounter, do you know ahead of time how that positioning and mapping system will work or not work? There's auditability, which is a big one in the age of modern artificial intelligence, because the neural networks that are driving a lot of these systems are incredibly complex. So can you audit the system and understand exactly what is happening behind the scenes? And this also relates to issues of like transparency. People complain a lot about the black box nature, to co-opt a term from aviation a little bit. But they complain about the black box nature of these big modern AI approaches, where it's a little hard sometimes, not impossible, but hard to understand exactly what is happening behind the scenes. Provability is another big one. So I'll talk a little bit later about how you can't have really substantially imperfect autonomous vehicles on the road. But a human driver, I think, makes a significant or maybe fatal mistake. I can't remember the exact statistic, around every 100 million miles, I think it is. So say 160 million kilometers. And so you can't really afford to wait and test and rely on that entirely. You need to be able to prove ahead of time that your system is likely to be safe, which is also extremely challenging. And then once again, you want guaranteed performance bounds. So you want to know that 99.999, whatever the number is, % of the time, your positioning system is accurate to within 10 centimeters or something like that. Another very substantial challenge. And there are standards for this, but this is something that everyone is working on. Probably the best one, which is a problem for everything, but especially in autonomous vehicles, is knowing when you don't know. So these are two sort of very simple scenarios. So you have a positioning system one, that is very accurate or fit for purpose 99.9% of the time, but lacks any sort of self-diagnosis or introspective capability. So it isn't able to analyze its own performance on the fly. And then system two is only fit for purpose 99% of the time. But of the remaining time, 99% of that remaining time, it's able to self-diagnose and understand that it's in trouble and ask for help or flag that there's a problem. And if you're making critical decisions based on these positioning systems, system two is far superior to system one, even though system one would be have a much better chance of getting published in a top academic journal because its absolute performance is better. And so these are some of the critical issues, and the field is dealing with this, but is still relatively immature, especially compared to areas like aerospace, in how it deals with these problems, partly because they're just incredibly difficult. I'm just checking, there's a chat, I'm just checking. Oh no, trolley problem, Kate. I'm not going to talk about that till question time. That's like clickbait. And then the final piece of the puzzle, or one of the other final pieces of the puzzle, is navigation and control. So human beings are remarkably sensitive to having acceptable acceleration and deceleration profiles when they're in an autonomous vehicle. It's amazing how sensitive you are to whether the vehicle is driving naturally or not. And there's a precedent here. So elevators and lifts have very clear standards on maximum allowable accelerations, for example. And it's the same for autonomous vehicles. There's been a lot of work on aspects of low-level control to make sure these vehicles drive in a way that humans will accept. It's actually remarkably noticeable when you get in a vehicle and it's not driving naturally. It's very discerning and sort of jolts you out of whatever else you're doing. As I said, I'm not just talking about technical stuff in this talk, and I feel an ongoing responsibility to just give people an insight into how surreal this whole autonomous vehicle AI robotics field has been over the last few years, because I think every time I tell people about it, I get told that people didn't realize how crazy it all was. My father worked in the aerospace industry in the 60s in the US, and the only other time we can think of where there was so much resources and focus in one area was the space race in the 60s. So just to give you one example, and this is all from publicly sourced documents or news articles. So there was an engineer who was working for Uber, and in the later court proceedings around some alleged theft of confidential materials, it was revealed that the bonus for this pretty young engineer was $157 million Australian, which is the bonus for an individual young engineer, which is just mind-blowing. Obviously, I'm picking on an outlier here, but the amount of money and in this field is not unlimited, but has been as close to unlimited as possible. And that is good in terms of motivating people to work on the technology, but it also has all sorts of on-flow effects, not all of which are good. And if you want to read up on this, there's a fascinating story. The money has an official term. It's known as funny money in the industry. It's basically when you have so much money that the actual amount doesn't really matter that much. And if you know there's an official term coined for it, you know that this is a widespread sort of thing in the sector. In this case, there's a fascinating story about what actually happened, an even bigger financial remuneration than this bonus was on hand. There was a court case, there was a bankruptcy case, and then there was even a presidential pardon most recently. So it's a fascinating story that sort of encapsulates some of the surreal nature of the autonomous vehicle field at this point in time. So where are we at now? There's been a massive consolidation of the key autonomous vehicle companies. So there's really only about 5 credible autonomous vehicle major companies that are primarily focusing on it. And then there's a bunch of automotive companies that are also investing in it, but are probably not leading the activities so much. And so some of these key companies are on this slide. And it's the usual story that the key development here is being led or has been led by tech companies, not by automotive companies, although automotive companies are catching up. And so I think I first rode in the Google self-driving car in 2012, which is that photo at the bottom left, and most recently rode in 2018 before they rolled out some of their most recent trials. There's been incidents. It's important to represent, I guess, a balanced, objective take on this. So you can argue that autonomous vehicles or autonomy-related tech has already prevented a large number of accidents in, for example, Teslas. But autonomous vehicles have also been involved in a number of fatal crashes as well. And so you can find lots of videos of fans of these technologies showing accidents that were prevented. Some of them, these are minor accidents. Some of these could have been major accidents. And then probably the first well-known fatality that was clearly related to some extent to the autonomous nature of a vehicle was in 2016. This got a lot of press at the time. Basically, an autonomous vehicle, a Tesla that was operating with autopilot, its sort of limited autonomy mode, was driving down a highway. Allegedly, the driver didn't notice a large tractor trailer that pulled across the highway several hundred meters in front. The autopilot system allegedly didn't recognize it as well. It went under the truck and the driver was tragically killed. And although the exact cause for this, I think you can read in the report, one of the speculations at the time was that because the vehicles were relying on vision primarily, there was a possibility that the back of the truck, it wasn't this exact type of truck, blended into the sky visually behind it. So if you're interested in this sort of stuff, there are very good NTSB and other transport authority reports into all of these incidents, which are worth reading. The biggest challenge isn't navigation, though. Navigation and mapping is a key challenge, but really the biggest challenge, arguably, for autonomous vehicles is human interaction. Humans are unpredictable, they're hard to predict, but we effortlessly do this. So we will probably drive by at nearly full speed. Perhaps the more cautious drivers would slow down and veer out a little bit around a pair of joggers, for example. But teaching a machine to not assume that they're just going to suddenly jump out in front of the car is very, very challenging, because in some circumstances, people will jump out in front of the car. So how can you differentiate between these? And corner case is another concept that you'll hear about a lot with autonomous vehicles. How can you deal with situations that have never occurred before in the history of humanity, but your car nevertheless would have to deal with? So there's a bunch of cartoon characters getting up and beating up someone. So training your systems to deal intelligently with this is quite challenging. And there's lots of on-flow effects. I mentioned the surreal situation in this area. Autonomous vehicles are not making money, or probably even arguably remotely close to making large-scale money for anyone, except in areas like mining, as I mentioned before. But these companies are nevertheless pouring incredible amounts of money into this field. And the amount of money and focus of talent, for example, is having a very big distortive effect on the field. So obviously there's been this massive exodus of top researchers from universities into these companies. These relationships are becoming a little bit more healthy or organic in terms of joint appointments between universities and companies. And there's sort of a lot of discussion about the suitability of those arrangements. Are they a good thing? Are they a bad thing? Are they somewhere in the middle? But essentially, it's really having a very profound effect on the whole research and development field internationally. Lots of consolidation. So lots of bigger companies have been buying up smaller companies. It used to be you'd hear about a new startup in autonomous vehicles literally every week. That has slowed down somewhat, but there's a smaller number of credible players in the area. Pulling from the UK's Guardian, there's ongoing skepticism. So the narrative about autonomous vehicles has changed from they will be everywhere in a few years' time to it's a very hard problem. It's going to take a lot longer than we think. We don't know exactly when they're going to be everywhere, although some companies are still predicting specific years and specific deployment numbers, which I think is courageous, because they get pulled up on it when that date actually ticks around. But there's still lots of investments. I peeled out two recently just from the Asian sphere of operations, where many hundreds of millions of dollars of raises for autonomous vehicle related activity. So if robo-taxis, so to speak, that carry people everywhere don't become widespread, there are alternative on-road options that may be more viable. So autonomous delivery is one. So this is Will Madden, one of our past PhD students. He worked at Oxford Robotics Institute in the UK, where Oxbotica came out of, probably most famously, but is now working for Neuro, which is a delivery company in the US. The two key advantages of autonomous delivery is there's no people on board the vehicle. So if you have any doubt in a safety situation, you sacrifice the vehicle and you break some eggs, you spill some milk, but that's fine because you're not injuring anyone. So your accident resolution solutions are much simpler. You just always prioritize the people outside of the vehicle. The other thing is if you have air conditioning or heating in the vehicle or refrigeration, if your deliveries take 4 hours to get across town, that is acceptable for a lot of customers because they just want it to rock up at some time during the day. You can't take 4 hours to deliver people across town. Passengers tend to not want a service that takes them 4 hours to get a few kilometers or miles across town. So there are some very key advantages of autonomous delivery that make it a more potentially tractable problem than robo-taxis. So if this holy grail, this sort of $1 trillion market of widespread robo-taxis doesn't become a reality, what are the fallback scenarios? Well, there's autonomous shuttles in your local community. There's autonomous delivery vehicles I've already covered. You could have robo-taxis that only work in, say, a retirement village or an airport, and more in off-road domains, so mining and defense and agriculture, for example, other big industries that might benefit more. The key thing to remember is the whole autonomous vehicle race that you see in the news all the time has been predicated on these sort of $1 trillion market projections. These other fallback scenarios will probably still earn the company some money, but it's going to be a much more mundane sort of business proposition. It's not going to be this sort of transformative technology that transforms cities everywhere. And this has a number of implications. This is an Australian-focused slide, but we've noticed the flow of talent behind the scenes is very indicative of how well a field is going. And a lot of talent has exited autonomous vehicle companies in the last probably 3 years, which is good for us in universities because we've got a little bit of our talent back and they've been enriched with experience from working in industry. But they've also gone to other fields in our area like robotics and artificial intelligence. So what about the future? So this is the classic hype curve, which sort of is a description of how technologies come onto the market. So our technology is first publicized, everyone gets really excited about it, and you have this peak of inflated expectations. Then there's the inevitable letdown where the technology doesn't work or doesn't develop as quickly, the trough of disillusionment, and then eventually some viable form of the technology comes out. This hype curve implicitly assumes the technology is eventually deployed in some form. So it is not always true. That is very important to note. So typical technology like voice recognition in your phone, it doesn't need to be perfect to make companies money. The first voice recognition sent your voice audio savings back to the cloud, and the cloud processed it, and that was viable. And then phones got powerful enough that you could do it locally on your phone. It's still not perfect. Voice recognition is not perfect, but it's good enough to be a feature in a commercial product. For general autonomous vehicle technology, the first thresholds for performance were things like logistics and ports, and then maybe mine sites. These are highly constrained environments, so they're a bit easier, and the technology doesn't have to be perfect. It just has to be good enough for the application. Maybe autonomous delivery vehicles that operate at slow speed will be the next key breakthrough there. That's not a prediction, disclaimer. I'm just giving you a hypothetical. The big problem with robo-taxis, or the challenge, is you can't deploy substantially imperfect robot taxis. The technology has to be pretty much perfect from the get-go once it's on our roads everywhere. And there are very few crutches or support mechanisms you can put in place to compensate for their shortcomings. That's the other key aspect. How close are we to this? No one knows, but there is a lot of resource being devoted to it. But there's huge uncertainty in terms of how we bridge this gap. You'll see well-known people like Elon Musk sort of debating about how to get to autonomous vehicles. And we don't know how large the gap is. We don't know how to assess it. So ending the talk with sort of the outcome, I'll start with the negative future and go to the positive future. So there is a scenario where if autonomous vehicles become everywhere, widespread, you actually have worse health outcomes. So everyone's talking about preventing accidents, which would be a great outcome. But you can imagine horrible scenarios where people don't walk or cycle anywhere and they just get in an autonomous vehicle. And in terms of heart disease and other things like that, there are models that show that there's the possibility of actually causing a lot of harm in terms of health outcomes from deploying autonomous vehicles. You could have an ultimate capitalist scenario where money buys everything, including traffic priority. If you pay more money, your autonomous vehicle gets routed through traffic faster than other poor people. And so you can imagine all sorts of not so good outcomes there. And one of the appeals of autonomous vehicles is an improvement in equity and accessibility to transport, which is possible, but if you don't look after it carefully, it could make the situation no better, and it could potentially even make it worse. Utopian future is you save 1 million lives a year, you save a much larger number of injuries per year, which would be fantastic. The whole nature of what a city looks like might be redesigned, the layout of the roads. You could get a massive reduction in the number of cars if people didn't own cars anymore and used autonomous robotaxis, although the cyclists in the audience will argue that you could rightly argue that you could achieve all of these changes by making cities more pedestrian and cyclist focused, whether or not there are autonomous vehicles or not, which is a very fair point. And my favorite, you could sleep during your commute, which is the ultimate goal for me. One of the things that technical people and research people and academics often get criticized for is they're head down in the research and in the technology, and they don't appreciate the bigger picture, right? And most of the time, this is a completely valid criticism. People need to be aware of the big picture more, the potential ethical and societal impacts of their work. However, this has been, I think, overcooked in autonomous vehicles. Because if the core technology and economic case for autonomous vehicles doesn't get to a sufficiently high level, it doesn't matter what else you do, they're not going to happen. So no amount of perfect regulation and perfect policy is going to compensate for the technology not being good enough. And so that's a key point to make. The regulation, the policy is incredibly important, but it is not going to enable or compensate for shortcomings in the tech. All right, so as Hugo and Kate mentioned, I will give away 3 copies of our just newly released Guide to Autonomous Vehicles. The reason for the title for kids and everyone else is when we did our first series of books for kids, we just got continually complaints that CEOs, grandparents, adults were really enjoying reading the books. So we made this sort of more general purpose for older kids and for adults as well. So we'll be giving away 3 copies of that. Once again, thank you so much for the invite to present. I think I stuck pretty much to my time. Thanks for turning up in the evening in the UK, and happy to answer any questions. Thank you.